Perfect. So we are Team Techionista. I'm Brenda, and I work together with Maaike. And we actually met a little over a year ago during a reschooling track called Techionista. But everything that we know about data science is really self-taught through courses and competing in these kinds of competitions. So let me show you what we did. We spent a good amount of time, of course, on EDA, and I can show you a lot of that. But pretty much the main things that we found is, yes, we have features with a lot of missing data. There's quite some big differences between the train and the test sets. We have some features in the test set that have 0 variance. And of course, we have some highly correlated features. Next step for us was data cleaning. But before we could actually start doing that, we decided to create a feature called building ID. Because we noticed that in the data set, there's some buildings that look very much alike. For example, this one that we show here. We believe this is the same building, and any missing values, for example, in the star rating, we imputed it by backward and forward propagation based on this building ID. So that's the main thing we did for data cleaning, but later on we also did all sorts of things with outlier detections and oversampling techniques, but I will not focus on that for now. Next step was feature engineering, and here we really tried a lot of different things, really trial and error. We tried, of course, different encoding techniques. We tried creating binary features. We even did some clustering of all the weather features. And in the end, we ended up with over 100 features, which is, of course, a lot. Which brings me to our next step, feature selection. And also here, we tried many, many different techniques. For example, we used a technique called VIF, a variance inflation factor. And this is very useful to detect multicollinearity in your data sets, because if you look at a Pearson correlation, it's really pairwise. But we also noticed that there are some sets of features in the data set that are highly correlated to each other. And of course, it's very useful to get rid of those. We also used the K-best, which really is a regression technique. And we used adversarial validation. And that's a really nice technique to use. I can show you a little bit more about it. What you really try to do with this technique is train a classifier to predict whether a record in your data set is from the train or the test set, which is this label here. Well, we did, and we ended up with a model with a very high AUC. And this pretty much indicates that the train set and the test set are very, very different. And that's, of course, not something that you want, because if you would train a model on the train set, it would have very different results on the test set. So the next step is then to look at feature importances of those features, and then you get rid of those. And it's really an iterative process. But the year factor, of course, is one of those features, because there's different years in the test set than in the train set. So that's our feature selection, and then we ended up with a set of features which we will train our models on. And that's really the phase that we are in now. This is pretty much our modeling approach. So we have different sets of features that we gain through the feature selection. And what we will do is train different models on those feature sets and on different parts of the data. For example, train some models on only a few years of data instead of the entire data set. And then we will combine the top models in an ensemble, and that should be our final prediction. Currently, our best performing model is a random forest. This is just some local validation scores of this model. You can see that also the linear models are doing quite well on this data set, but they have a bit higher variance between the different validation sets. So we found that the random forest so far is working quite well. Yes, and then the final step that's also ongoing, of course, but that's model evaluation. And for this, we like to use SHAP, which is a technique that you can use to assess the global importance of your features. Well, here we created a feature, it's called factor B, which is related to the building ID that we created. And of course, it's very important. So this feature set is really useful to detect on a building level. And what's also nice about SHAP is that you can use it to really explain the outcome of individual records. So for example, here, this is a waterfall plot. And how you should interpret this is that our baseline model predicts a score of 82.9, but because of the features in this record, so this particular star rating of 61 or this particular year factor 2, it actually predicts an outcome of 60.9, which is really close to the actual label, which is 60.7. So for us, this is an ongoing project. We are still working on improving our models and doing more tuning. We haven't done any of that, but so far we are very happy with the results. So that's the end of our presentation.
I'm going to present our teamwork code for climate action. You know, the other day, yesterday, each one of us, we were looking for a new friend. We were looking for someone to team up. And that was a great experience. And that was our first Kaggle competition. Okay. You know, in this data set, we had, I think, 63 features. And we believe that it is a good try, a good experience to do, to check the Occam-Razor principle, to reduce the dimension, to use fewer features. For that, we use LightGBM. It is possible. LightGBM is a boosting learner. It has a lot of trees. It's going to use different number of times each features in the model, and it's going to rank them according to the number of time each feature were used in the model. And we check the distribution without, okay, for the start, we could start with the first top 7 features. By first top 7 features, we got in the leaderboard shape of the Kaggle, we got a place close to 100. Then we reduced that to 4 features because according to the number of times that this feature were used in constructing a model by LightGBM, they had a greater distribution. We got in the leadership board, we got a place close to I think 90 by 4 features. I was playing with features. I thought, okay, if I remove the energy star rating, what will happen? And the result was surprising. After removing the energy star rating and just working with 3 features, we got a place close to 30 in leadership board. You know, for pre-processing or for feature selection, or to find out which features have the most impact on the prediction, we use the LightGBM. But for constructing the model, we use random forest. We got our best result with random forest. We checked k-nearest neighbor, we checked boosting learner such as XGBoost, but as you know, XGBoost or LightGBM, they have a lot of parameter and it is time consuming to tune a lot of parameter. Anyway, we got our best result with random forest, and that's it. Thank you for your attention.
Thank you. There was a short presentation. So then the audience and our jury team will have 2 minutes more to ask questions.
Yeah, that's good. You know, I wanted to talk about the golden rule, the thing that had the most effect on our result, and that was really surprising. Out of 63 features, we could get a good result in leaderboard ship just by 3 features. That was interesting for me at least.
Can you see the screen?
Yes.
Okay.
Very good.
Okay. Was? Achso, du kannst hier weiterklicken, glaube ich. Nee. Sorry, we started in a minute. Okay, we're not sure how to move on to the next slide. Da? Nee. Okay, we got it.
Yeah, we fixed.
To start
okay.
off, we found out that the feature energy star rating has the highest prediction potential. Like you can see in the bottom, there's the mean absolute scores of the explainable boosting machine. we did, and we have the highest score on energy star rating. So we looked at this feature more and found out that it has a high number of missing values. So we tried 3 different approaches to tackle this problem. First, we started with a simple approach. We just set all the missings to the average value. It worked okay, but we thought it could do better. The second approach was that we found out that the average energy consumption in this missing energy star ratings was about 6% higher than the average cases. So our solution was to put to the average rating of the missing values, we adjusted it by 6%, and this actually did the best results of our approaches. For the third approach, we built a submodel for the missing energy star rating with a random forest on the building specific features. Yeah, we had actually promising results, but we thought we had to do further submodel optimization. But yeah, we lacked the time, so we used the second approach.
Hi everyone. I will talk about the bias that we found in the data. That was the state 6. And we saw in the data that state 6 is very prominent. And after looking at the data, we saw that in other states, the multifamily buildings are categorized, have labels, and in state 6, it is uncategorized. And another thing that we found is that energy star rating in state 6 is very high and densely distributed in comparison with the other states. So we tried to train the data and enable the model to learn the state bias, the state 6, and then we found out that this is having better results. The second approach that we tried was to do cluster analysis, which we did over K prototypes, and we found out that there is one cluster. We divided the data in 5 clusters, and we found out that one cluster has most of the data from one cluster is state 6. And we tried to run our models on without this cluster after eliminating the data set. However, that reduced the performance of the models. So our thought is that we would need to make a finer clusterization, and it would make sense to try it without state 6. However, we didn't do that, and we chose the approach 1 because the results were better.
And then lastly, for the model selection, we thought about using some kind of time series model, but because we didn't have a building ID, we didn't think that it would make much sense to go over the time series. And we also thought about that you could build a building ID, but we didn't go down that route further because of no more time. And so we tried out other models. We used an explainable boosting machine, which you already saw on the first slide, where we found out the high importance of the feature with the star rating. We tried a multi-layer perceptron, we tried random forest, and we tried gradient boosting. And we worked a little bit in parallel. So in the beginning, we actually used all features available, except for the wind features, which we already opted out really early. And on that, the models were all pretty similar, but all not very good. So then when we had a selection of first 13, and then when we put the state factor back in, 14 features, the gradient boosting algorithms or models were all a lot better than the other ones, so we stick with those. And then we also tried if we tried with cat boost and with XG boost, and the XG boost was better than the cat boost, but there was also trial and error. And then we chose the parameters with checking out if the bias is getting too high. Also something that we had to think about was reasonable training time. Obviously, you can put a really high number of estimators, but then we don't have big calculating machines. So we had to take training time, so we went with 4,000.
Sorry for the interruption. Can you finish like in 20 seconds, if that's possible? You're over time. Yeah.
Actually, this is the last slide, which
Okay.
is only our the last thing we used at the last parameter selection. And 31.076 was the factor we got. And
okay. Yeah, thank you very much. Hello.
Yeah, so Anjali will share the slides and I will start with the presentation and she will continue later.
Yeah, great.
Okay, yeah. First of all, we just started yesterday working on that, and we have some freshmen in our group and newbies. And so for me, that was a totally new experience, and that was a lot of learning while doing. Therefore, it might not be the best data cleaning possible, but we tried our best and we did as much as we could. Okay, so regarding the data preparation, we first, of course, had a look on all the distributions, the variables, the categorical, the numerical variables. We had a specific look at the facility type, for instance, because we noted that this has many different categories and would just inflate the number of features once we encode the labels. So we collapsed facility types that looked similar regarding the labels that we identified. And next, we had a look on the numerical variables on the next slide. Yes, and here we just had a look on the distribution and outliers and decided not to remove outliers because just in one case we did remove them. In the year build, because we noted that some years were given as 0, and that must clearly be a mistake. So we first replaced them with missing values and imputed them later. We also checked whether we have variables with low or no variance, and we saw 2 of them on the next slide, and we excluded them as well because they had, at least in a test data set, they had almost no variance at all. And one of them had actually 0 variance. We looked at the correlations between all the numerical features and excluded some of them that seemed to correlate quite high and contained a high share of redundant information. Like, for instance, we excluded a full array of minimum temperatures over year, for instance. We created 3 new features because we thought that the stability of weather over the year might have an influence on the results. So we created the variance of the minimum, the maximum, and the average temperature over year, and added that to the model as well. And okay, that was on the next slide, Anjali. So I'm a bit rushing. So and then in the next step we did the imputation. We checked for missing values and we imputed missing values. So we identified a high share of or some considerable missing values in the year build variable. We replaced it with a median. And for the energy star rating, we decided, since there were so many missing values, to use the k-nearest neighbors imputation and not just the mean or median value. But for some of the variates, we just dropped them because, as others have pointed out before us, they have such a huge amount of missing value that they wouldn't be of use for the model. And that is all for the data preparation. And now Anjali will continue with the model.
Hi, everyone. So for the model, we went for the strongest regression models we know, which are the boosting methods, XGBoost, CatBoost, and LGBM boost. The main difference between XGBoost and light GBM boost is basically the first one grows depthwards, And the second one is leaf-wise growth. So both essentially do the same thing, but the point of including the three models is boosting can often create a bias because they can like overtrain. But when we introduce three boosting methods, and for each of these methods, we give a weightage. So we trust the CAT boost, XGBM and LGBM regressors a certain amount, and their results are weighted and like brought together. And then we have one single result. So when we do this, we bring in variance because now our boosters, which would essentially be biased, are there are three of them, and each of them could give a different result. And yeah, so now we take care of the bias here. And this was our final results. With cross-validation, we got a 37.1 with an 80-20 split. And on our final submission, we had a 33.68. But even then, like our final submission was again 80-20 split on the entire data set. We unfortunately could not make the submission. So it's still running. And that is it. Thank you.
Thank you very much. You're just on time. Perfect.
So I'm Katrin from the team Climate Warriors, and Lina and I are like the members of the team. We are both from Maastricht University, and yeah, that's where we know each other from. And unfortunately, Lena is ill today. That's why she was only working with me yesterday, but I'm still very happy that I get the chance to present what we've done so far. This was also our first Kaggle competition that we tried out, and yeah, we get quite similar like results to some other teams, so I hope it's not too boring, but yeah, I'm just gonna start. So for data preprocessing, we were also looking at the missing values in the data set, and especially also in the test data set, where we also found out that the wind speed features had a lot of missing values. That's why we decided to discard them. Another, like as the others already said, the energy star rating also has quite some missing values, and we tried to impute these missing values with just a simple missing value imputation. Yeah, and discarded the other features with a lot of missing values. Yeah, the imputation for energy star rating is also very important, as it's highly correlated to the site EUI feature that we're trying to predict. Then we did some outlier detection, and in the end we decided to go with a local outlier factor to reduce the outliers. Yeah, we also tried out another one, but like the forest one, but this one worked better. Then we moved on to the feature selection. Here we used a decision tree regressor, and after some tests, we decided to select the 20 features with the highest scores. For that, yeah, within these features, there are also two features which we created by ourselves with feature engineering. That's the minimum annual temperature and the maximum annual temperature, where we just took the minimum temperature of all months and the maximum temperature of all months, where, yeah, you could also see in the picture, like in the correlation matrix, that that made kind of sense to maybe, yeah, take these features together and create new features. And then finally coming to the model, we just had a look at the three different boosting models, XGBoost, LightGBM, and CatBoost. So how they were performing. And then we decided to go with the model which had the best score, the XGBoost. We did some hand tuning of values, but nothing more. Yeah, that was basically what we've done in the last 2 days. Thank you.